Imagine waking up one morning, stretching your arms, looking out the window, and realizing that everything you have ever known, your room, your street, your planet, your entire cosmic neighborhood, might actually be the inside of a gigantic soap bubble. And not even a special bubble, not some fancy handcrafted bubble made by an artisan physicist, but just one bubble among who knows how many others, drifting in a cosmic bath that makes our whole universe look like the world's most fragile aquarium decoration. It is the kind of idea that slips into your brain the way a rogue balloon floats into a birthday party. Unexpected, slightly unsettling, and impossible to ignore once it arrives. Because if the universe truly is a bubble, then you and I are basically living in the cosmic equivalent of a shimmer on a film of soap, hoping no one comes along and sneezes too hard. Good evening, curious minds. I truly hope you will enjoy today's video. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift toward sleep, consider subscribing, but only if you enjoy these calm journeys through the universe. Now, let's begin. But let me slow down before you imagine the universe popping with the same terrifying speed as a bubble meeting an enthusiastic toddler. This bubble idea is more than a cute metaphor. It is one of the strangest and most fascinating scientific possibilities ever imagined. Scientists entertain it not because they want to ruin our day, but because the evidence we do have about the cosmos hints that our universe might not be the whole story. In fact, it might be only the tiniest fraction of something exponentially bigger, stranger, and wider than anything our telescopes could ever hope to see. And that is saying something, considering we built telescopes that can spot galaxies so far away their light started traveling toward us when dinosaurs still had worries like asteroids and bad weather. The idea of a bubble universe comes from looking at the sky and realizing that space seems to have a weird talent. It stretches. Not politely, like a cat getting ready to nap, but in a way that makes entire galaxies race away from us as though we just told them the check is coming. Space expands, and not slowly in a leisurely Sunday afternoon way, but in a way that has convinced scientists that something extraordinary must have happened long ago. If space has been stretching this whole time, then maybe the universe is not a giant static room, but a dynamic balloon that has been inflating since the moment it began. Now, here's where things get interesting. If our universe can inflate like a balloon, then what is to stop space from creating more balloons? Imagine a cosmic bubble bath full of growing bubbles, each expanding on its own, each with its own interior, each sealed off from the others. You would not be able to see the other bubbles from inside yours. It would be like living inside a snow globe without knowing other snow globes exist on the same shelf. A shelf so enormous it might make your brain want to gently back away and reconsider its life choices. And the funniest part is that we might never know for sure, because the supposed walls between these cosmic bubbles are not walls you can touch or knock on. They are more like the boundaries of a dream. You experience everything inside, but you can never walk out to see what lies beyond. Our universe keeps everything outside its horizon locked away like a cosmic spoiler alert. It is the universe's way of saying, you can explore, but you cannot explore that much. Which feels unfair, considering we have spent centuries building metal tubes just to escape Earth's gravity for a few minutes at a time. Still, something about the idea of being inside one bubble among many has a weird kind of comfort to it. For one thing, it makes our universe feel less lonely. Instead of being a solitary island floating in a dark ocean, we could be part of a vast cosmic archipelago. Maybe somewhere, in some distant bubble, there are stars arranged into spirals we never imagined, or planets covered in colors that do not exist in our language, or creatures wondering if they are the only bubble in the bath. Picture alien physicists pointing lasers at their sky, running equations on their alien whiteboards, sipping whatever aliens sip, and coming to the same uneasy conclusion. Yep, we are probably living in a cosmic bubble too. It is a strangely unifying thought. You could also imagine the bubbles drifting near one another, swirling gently in some cosmic current, not touching, but existing together like soap bubbles floating above a sink. And if that is true, then our universe is not the whole story. It is just one chapter in a library so large that calling it infinite would feel like an understatement. The idea expands your mind the way space expands itself, stretching curiosity until it feels wonderfully, impossibly wide. The most mischievous part of all this, of course, is that our entire bubble might be just one tiny shimmer of something we can never see. A soap bubble inside a bath that exists inside a house, that sits inside a city, that exists inside a universe so vast no metaphor can capture it. And somewhere, maybe, a cosmic child is blowing these bubbles simply because making universes is fun. Or maybe not. Maybe we are the only bubble. But that would almost be stranger, would it not? And so the hook is simple. The universe may not be the universe. It might just be ours, one bubble in a frothy ocean of cosmic possibilities. And once you start thinking about that, it is very hard to stop. If you have ever tried to look over a tall fence to see what your neighbors are doing, strictly for scientific purposes, of course, you already understand the emotional core of cosmology. Humans are curious creatures. We want to peek, to explore, to press our noses against the glass of reality and ask, what is out there? But the universe, in its infinite cosmic mischief, has built a fence around us so enormous and so immovable that even the most determined astronomer cannot climb it. That fence is called our cosmic horizon, and it exists because light, the messenger of the universe, is just not fast enough to deliver every postcard the cosmos has ever written. Imagine standing at the center of a colossal dark field, holding a flashlight that turns on at the moment you are born. As time passes, the light spreads farther and farther, illuminating more of the field. The illuminated region is everything you can possibly interact with. Beyond the edge lies an endless expanse you cannot see, touch, or even sense. That edge is your personal horizon. Our universe operates in the exact same way, except instead of one person with a flashlight, we have an entire cosmos turning on its lights at the moment of the big beginning, and instead of a quiet field, We have space expanding like it drank 20 espressos and decided now is the perfect time to grow. Now here is where it gets delightfully tricky. Light is fast, incredibly fast, the universe's most punctual messenger. But space itself does not care about speed limits. Space can stretch faster than light can travel. If the universe wants to expand, it expands. Light can try its best to cross that stretching distance, but sometimes the finish line keeps moving away faster than the runner can sprint. The result is a boundary made of pure limitation. We can only see the part of the universe whose light has had time to reach us since everything began. Anything farther away is sending signals that will never make it across the constantly lengthening track. This creates a strange situation where the universe is vastly larger than anything we can observe. We live inside a spherical region defined by the fastest thing in existence, yet even that fastest thing cannot keep up. If the universe was a movie theater, we would be stuck in the middle seats, unable to see anything past the row in front of us, except the row is constantly moving farther back each time we blink. And no matter how powerful your telescope is, no matter how much money you pour into it, or how many cool acronyms you give it, it will not allow you to see beyond this cosmic boundary. A telescope cannot bribe physics. Many have tried, mostly by suggesting bigger mirrors. The cosmic horizon is not a wall you can smash through or a veil you can lift. It is simply the limit of how far information has traveled. Beyond it, we have no data, not even a whisper. The universe could be dancing a cosmic tango just beyond our line of sight, and we would never know. There might be galaxies spinning in ways that would make our astrophysicists weep with joy, or stars exploding in a style so dramatic it deserves its own reality show, or entire regions where the laws of physics have decided to take creative liberties. But from our point of view, it is all sealed behind a curtain woven out of time and light. One of the most mind-warping implications of this horizon is that even the things we can see today were once much closer. Because space expands, distant galaxies did not always live at those distant addresses. It is like waving at a friend across a river only to discover the river widens every second. Eventually, your friend becomes a colorful dot, then a speck, and then disappears entirely. Not because you moved, but because the river grew faster than your message could cross it. This is the cosmic version of long-distance relationships not working out. And yet, despite this limitation, everything we do see paints a picture of a universe that continues far beyond the cosmic edge. The galaxies we observe close to that limit appear younger and stranger, stretched by extreme distance, like looking at the universe through time-traveling binoculars. They hint that there must be more beyond them, vast regions we cannot explore because light has simply not had enough time to visit us from there. So we stand at the shoreline of the observable universe, watching the waves of ancient starlight roll in, knowing there is an ocean beyond that we will never sail. The most humbling part is that this boundary grows as time passes. As the universe ages, light from farther regions finally reaches us, expanding our visible bubble. It is like the universe slowly lifting the blinds bit by bit, showing us more of the cosmic scenery, but never all of it. The horizon is not a fixed limit, it is a moving frontier. The universe is generous, but it is also patient. Very, very patient. So we look outward knowing that beyond what our telescopes capture lies a realm forever out of reach. Not because of lack of effort, but because that is simply how the cosmos works. The universe is vast, and light can only run so fast. And so we remain inside our cosmic bubble of visibility, peering outward, wondering what lies past the edge, knowing that our horizon is not the end of everything. It is merely as far as the universe will currently let us see. Picture the universe in its first trillionth of a second. Actually, do not picture it. That would be like trying to imagine a hummingbird flapping its wings fast enough to generate a small hurricane. The early universe was so absurdly energetic and so impossibly tiny that our best mental images start leaking sanity the moment we attempt them. But we can try. Imagine a speck, smaller than anything you have ever considered, smaller than the smallest thing you have ever heard of, smaller than even the word tiny feels comfortable describing. Inside that speck, everything that would eventually become galaxies, planets, atoms, you, me, sandwiches, and romantic comedies was squeezed together in a state of pure, pressing tension. Then something happened, something so dramatic that calling it expansion feels like calling a volcanic eruption a warm breeze. That something is cosmic inflation, the universe's version of slamming the gas pedal so hard that the pedal nearly exits through the floorboard. Inflation was not slow or gentle. It did not quietly unfold with cosmic grace. It was more like the universe panicking at the sound of its own alarm clock and exploding outward in every direction at a speed that makes fast sound like a bad joke. Space multiplied itself exponentially, doubling and doubling and doubling again so quickly that within a blink, if blinking had existed, sizes leapt from unimaginable microscopic scales to something large enough to hold the idea of galaxies someday. Now, here is where things take a delightfully strange turn. Inflation was not just rapid, it was unstable. Think of it like a pot of boiling water, bubbling and foaming, except instead of water molecules, you have space-time itself frothing with energy. In this bizarre state, little pockets of the inflating universe could stop inflating while surrounding regions kept ballooning outward. When one of these pockets slowed down, everything inside it had a chance to cool and form stuff, particles, atoms, stars. That pocket became a universe, our universe, a bubble universe. But inflation does not like to stop everywhere. It stops here and there, but in between those calm pockets, space-time keeps inflating like a cosmic loaf of bread that refuses to finish rising. So pockets freeze, become universes, and drift apart. Meanwhile, the surrounding inflating space expands even faster, dragging these pockets far from each other, isolating them completely. Then more pockets freeze, and more, each one sealed off by vast regions of space expanding so violently that no message, no light, no cosmic traveler could ever cross from one bubble to another. It is a cosmic assembly line churning out universes like a factory that misplaced its off switch. In this picture, you end up with not one universe, but an endless frothy sea of them, each born from its own little pause in inflation's furious growth. Some pockets might be enormous, some tiny. Some might last for billions of years. Some might extinguish themselves quickly, like cosmic fireworks that do not quite make it to the finale. Each universe would have its own properties, its own mixture of matter, its own strengths of forces, its own ways of forming stars. In one bubble, gravity might be gentle and patient. In another, it might be extremely enthusiastic, pulling things together the moment they try to drift apart. The inflationary process does not only build universes, it builds diversity on a scale so unimaginable that words lose their grip trying to describe it. Our own bubble sits inside this frothing sea, oblivious to its neighbors. We will never see them, not because they do not exist, but because they are locked away behind regions of perpetually expanding space. The distance between bubbles grows faster than communication can travel, faster than any attempt at cosmic teamwork could ever succeed. If universes could wave at each other, the gesture would never arrive. They are isolated by the very process that birthed them. The incredible twist in this story is that inflation solves puzzles about our universe without even trying. It explains why everything looks smooth and uniform on enormous scales. Inflation stretched any early irregularities so widely that they smoothed out like dough under a cosmic rolling pin. It explains why the universe is flat, because inflation expanded it so dramatically that curvature became practically undetectable. It explains why the cosmic microwave background appears nearly the same no matter where we look. Inflation is like the universe's all-purpose problem solver, though it accomplished all this while behaving like the most reckless expansion event imaginable. But inflation also leaves behind the faint imaginative possibility that our universe is not singular or privileged. It might be one bubble birthed in a moment of cosmic frenzy, surrounded by countless others blowing up into existence in an ongoing process that may still be happening now in regions we will never witness. So when we talk about cosmic inflation, we are really talking about a moment when the universe breathed in, panicked, and doubled itself into a wild, unstoppable frenzy. And in the chaos, little islands of calm appeared, each one a universe. Ours is just one of them, floating in a sea we cannot cross, the product of a burst so powerful that its aftershocks may still be churning out fresh universes, like sparks flying from a cosmic firework that never burns out. Inflation is not merely an expansion. It is a cosmic origin story with a twist. The universe did not just boom into existence, it multiplied, branched, blossomed, and may still be doing so. And if that does not stretch your imagination, then your imagination might need its own round of inflation too. If cosmic inflation was the universe's wild beginning sprint, then eternal inflation is the moment the universe said, "Actually, why stop running?" and kept going indefinitely, as if the cosmos enrolled itself in an infinite marathon with no finish line, no water stations, and absolutely no intention of slowing down. Eternal inflation takes the already mind-bending idea of rapid expansion and kicks it into an even stranger gear. Instead of imagining the universe inflating once in a single dramatic burst, picture inflation as a permanent background hum, a cosmic vending machine that keeps producing new universes the way an over-enthusiastic parent keeps supplying bubble gum long after the kids have reached the please no more sugar stage. The basic idea is deceptively simple. In certain regions of space-time, the inflationary process never fully ends. It pauses here and there, creating pockets that cool down and stabilize. Those pockets become individual universes, but everywhere else, the expansion continues unchecked. And not in a lazy, slow motion kind of way. It expands exponentially, relentlessly, like a magic trick that repeats itself faster than you can blink. Each time inflation relaxes and forms one universe, the space around it inflates even faster, creating room for more pockets to appear. The result is a ceaseless, bubbling cosmic froth, a kind of eternal cosmic yeast dough that never stops rising, stretching, and generating new universes in its wake. Imagine standing in an endless field of tall grass as a fierce wind blows through it. The wind never stops, but occasionally a small patch of grass is sheltered, stopping its swaying for a moment. Each sheltered patch is a universe, calm and stable, while the storm of inflation roars on everywhere else. Over time, countless such pockets appear, scattered throughout the inflating landscape, isolated from each other by the relentless stretching of space. The more pockets that form, the more the surrounding space-time expands, making each new universe drift away so rapidly that they become permanently out of reach. The parent never stops buying gum, and every piece gets thrown farther than the last. One of the strangest consequences of eternal inflation is that it suggests the cosmos is not a single grand stage where everything unfolds. Instead, it is a backstage warehouse full of smaller stages, each with its own lighting, props, actors, and scripts. The action inside one bubble universe could be wildly different from the activity in another, because each bubble inherits slightly different conditions from the moment inflation lets go inside it. It is as if every tiny region of space-time pulls a random cosmic lottery ticket before becoming a universe. Some tickets lead to galaxies, others to more exotic outcomes. Some universes might never make stars at all. Some might make so many stars that the sky would look like an over-decorated holiday card. Now, you might imagine all these universes floating politely beside each other like bubbles in a child's bath, quietly minding their own business. But the real picture is far more chaotic. Eternal inflation is not a serene bubble bath. It is more like watching boiling water, where each bubble forms, rises, and gets carried away by a furious current of expanding space. And because the inflationary expansion between the bubbles is so incredibly dramatic, each universe becomes not just separated, but permanently sealed off from every other. Even if two universes formed side by side, space would stretch so violently between them that any hope of communication would be gone almost instantly. It is cosmic social distancing to the highest possible degree. Meanwhile, the larger space-time in which all these bubbles form is still inflating, That means that even as pockets of calm appear, the inflating regions grow faster than new universes can form. Paradoxically, the more universes inflation creates, the larger the inflating space becomes. The cosmic loaf keeps rising faster than you can slice it. This makes eternal inflation an unending process, with no final universe, no ultimate destination, and no maximum capacity. It is a cosmic production line with infinite ambition and absolutely no management oversight. From a philosophical angle, eternal inflation takes the idea of the cosmos and turns it inside out. Instead of the universe being everything, it becomes just one outcome. Instead of thinking of reality as a single stage, we now have an entire warehouse of stages. Instead of imagining space as finite or even infinite but unified, we imagine an infinite expanse endlessly generating vast, isolated pockets of reality. It is the difference between reading one book and discovering that the library has no walls, no ceiling, and no librarian to say, "Sorry, that section is closed." One of the most intriguing parts of eternal inflation is how it reframes the question of origins. You can ask how our universe began, and physicists can trace that beginning to the moment inflation ended locally. But what about the larger inflating space that gave rise to us? Did it begin? Or has it always been there, bubbling with new universes the way popcorn kernels keep bursting long after you hear the first pop? In eternal inflation, beginnings become relative, not absolute. Our universe has a beginning, but the cosmic process that created it may be timeless. A parent who has been buying gum forever and shows no signs of stopping. And perhaps the wildest idea of all is this: if eternal inflation is correct, then somewhere out there, new universes are forming right now. Not nearby, not visible, not accessible, but happening nonetheless. Entire cosmic bubbles are flickering into being, cooling, expanding, growing galaxies, forming stars, and building histories we will never witness. While we sit here wondering about the cosmos itself might be busy crafting new realities in the background, as casually as a baker tossing fresh loaves into the oven. In eternal inflation, creation is not an event. It is an ongoing habit, a cosmic reflex, a perpetual storm of expansion that ensures the birth of universe after universe after universe. And whether we like it or not, we are just one bubble in that endless, unstoppable froth. If the universe had an artist, it might not be a wise old sculptor or a cosmic engineer with neatly labeled blueprints. It might be randomness, pure, unapologetic, unpredictable randomness flickering at the smallest scales imaginable. The kind of randomness that cannot decide between yes or no, so it picks both, shrugs, and calls it quantum behavior. In the realm of the incredibly tiny, uncertainty is king. Tiny fluctuations jitter, pop, shimmer, and vanish faster than you can say, "Why is the universe like this?" Yet these tiny flickers may be responsible for everything that exists: galaxies, stars, planets, oceans, brains, sandwiches, heartbreak, poetry, and the vastly complicated things humans do when left alone with their thoughts. To understand how randomness sculpts worlds, we have to journey down into the quantum foam, the lowest floor of reality where nothing sits still. Even empty space is not really empty here. It is more like a restless stage where particles appear and disappear so quickly they barely qualify as guests. Quantum fluctuations behave like cosmic hiccups, brief interruptions that come and go, but leave behind the faint memory that something stirred. They bubble up constantly, even in total vacuum. And though each individual fluctuation is tiny and fleeting, together they form a chaotic background hum that never stops. Most of the time, these fluctuations stay tiny and harmless. But in the early universe, when everything was squeezed into a minuscule volume under intense conditions, these quantum jitters mattered. They were magnified by the rapidly expanding space-time. A fluctuation the size of a whisper could be stretched until it shaped vast regions of matter. A tiny unevenness in density became a cosmic seed. One region held slightly more stuff, another slightly less. Over billions of years, those tiny differences blossomed into the grand architecture of the cosmos. Clusters of galaxies in one place, empty voids in another. Without randomness at the start, the universe would be as smooth and featureless as a freshly cleaned countertop. Pretty, but not particularly interesting. In a sense, we owe our existence to these tiny quantum quirks. Every star that burns, every planet that forms, every molecule that dances, every life form that wonders why the universe is so big, all of it traces back to random bumps in the earliest moments. We are built from the consequences of microscopic cosmic indecision. It is as if the universe rolled countless dice at the beginning, and we are living inside the results. That may sound unsettling, but it gives the universe a certain creative flair. Instead of being constructed from rigid blueprints, reality emerged from a kind of improvisational jazz played at the smallest scales. But quantum fluctuations have an even wilder possible role, one that stretches the imagination far beyond the familiar. In some theories, a random fluctuation in the quantum field could be responsible not only for shaping stars and galaxies, but for giving birth to entire universes. At first glance, that sounds like a plot twist stolen from a science fiction story. But in physics, quantum fields permeate all of space. These fields can store energy, shift states, and, under very special circumstances, trigger wild, runaway events. If a fluctuation pushes the field into a particularly energetic state, the surrounding space could suddenly expand at enormous speed, like a cosmic engine roaring to life. Such a burst might create its own bubble universe, separating from the surrounding space and becoming an entirely new cosmic realm. Once that bubble forms, it evolves on its own, free from influence by the outside. Its space-time stretches, cools, and forms matter. From the perspective of its inhabitants, who might someday wonder about their origins, the universe seems to begin from nothing, without knowing it started as a tiny quantum flutter in some larger cosmic field. Meanwhile, outside their bubble, the original space-time continues on, perhaps producing more fluctuations, more bubbles, more universes. This idea makes randomness not just a sculptor of structures, but a cosmic architect that draws up entirely new realities. It suggests that the laws of physics themselves might be products of chance. Different bubbles formed by different fluctuations might inherit different properties, ending up with different strengths of forces or different patterns of matter. Some universes might expand too quickly for stars to form. Others might collapse immediately. A few, perhaps a very lucky few, might find themselves balanced just right, stable enough for galaxies, complex enough for chemistry, and hospitable enough for creatures who can wonder about where they came from. If randomness is truly the architect behind everything, then our universe is not the carefully crafted product of a grand design. It is a snapshot pulled from an infinite deck of quantum possibilities. We exist because one early fluctuation nudged reality in a particular direction at a particular moment. Change that moment, and everything might be different. Our cosmic story is built upon a jitter, a twitch, a flicker, something so small you would never have noticed it if you were there to see it, which of course you could not be, since you owe your existence to it. This might sound like the universe is chaotic or unreliable, but there is something strangely poetic about it too. Randomness gave rise to order. Noise led to structure. The unpredictable birthed the stable. The universe took uncertainty and used it as the foundation for galaxies and stars, and eventually for minds capable of pondering uncertainty itself. In that sense, randomness is not just an architect. It is a storyteller, weaving complexity out of chance. So the next time you feel like life is unpredictable, remember, the entire cosmos is built on unpredictability. And against all odds, here we are, shaped by quantum jitters, living in a universe carved from randomness, contemplating the very fluctuations that made us possible. Imagine strolling into a cosmic hardware store where every aisle is dedicated to the laws of nature. One shelf displays versions of gravity, mild, strong, misbehaving, and please do not use after midnight. Another shelf is packed with different strengths of the electromagnetic force, each one promising to hold atoms together in its own charming or alarming way. And somewhere near the back, past the clearance section, you might find the settings for how fast light is allowed to travel. Our universe appears to have grabbed a very fortunate combination from these cosmic aisles. But if the multiverse exists as a sprawling collection of bubble universes, then each bubble might stroll down the same shelves and choose a completely different set of rules. Some universes might play by physics we would recognize, while others might operate on principles that would make our scientists feel like they accidentally stepped into an improv comedy show where no one told them the script changed. In our universe, gravity follows a predictable script. It bends space-time, keeps planets orbiting stars, and occasionally reminds humans that dropping their phone is a terrible idea. It is reliable, stern, but fair. Yet in another bubble universe, gravity might not follow this well-established routine. It could be impatient and overly strong, yanking matter together so aggressively that stars form in seconds and collapse just as fast, like celestial stress balls being squeezed to their limits. Or it could be so weak that matter barely holds itself together at all, resulting in a cosmos where atoms float apart like they are practicing social distancing at the highest possible level. The result would be a universe so ethereal and dispersed that nothing larger than a dust mote could ever form. This is where the fun begins. If gravity can vary, so can everything else. Quantum fields, the invisible stuff that defines how particles behave, might vibrate differently in another universe, producing particles unlike any we know. Maybe there are universes where electrons are heavier or lighter, or slightly embarrassed by how many responsibilities they have. Maybe there are versions of reality where protons refuse to stick together, leaving the universe with no atoms, no chemistry, and no chance of forming anything more complicated than a lonely field of energy humming to itself. Other universes might have forces that do not exist in ours at all. Maybe there is a universe with a fifth force, a hidden friend to gravity, electromagnetism, and the strong and weak nuclear forces. In that universe, objects might move in ways that would look like magic to us. A falling apple might zigzag. A thrown rock might loop back to its owner. Entire galaxies might swirl into shapes so bizarre that our astronomers would need a support group to discuss what they were seeing. But let us get even stranger. Imagine a universe where time flows differently depending on where you stand. Move one step to the left, and clocks tick twice as fast. Move one step to the right, and time drags like a boring lecture. In another universe, time might not flow at all. Events could be static, frozen, like a cosmic slideshow with only one slide. In yet another, time might constantly branch and fold, turning reality into a labyrinth of overlapping moments where cause and effect get tangled like headphone cables in a backpack. If you are wondering whether life could exist in these strange universes, the answer is probably not in any familiar sense. Life as we know it depends on delicate balances. Too much force or too little, too fast or too slow, too chaotic or too orderly, and the whole recipe falls apart. But just because a universe seems uninhabitable to us does not mean it is uninhabitable in principle. In a universe with different rules, life might emerge in ways we cannot imagine. Perhaps creatures arise from energy patterns rather than atoms. Maybe intelligence exists as ripples in space-time instead of physical organisms. Or maybe consciousness floats freely, unanchored by bodies or matter, like ideas drifting across a blank canvas. Some universes might be extremely short-lived, popping into existence and disappearing almost instantly, their physics too unstable to persist. Others might endure for trillions upon trillions of years. A few might experience cycles of expansion and contraction, bouncing like cosmic trampolines. Some might look visually stunning, filled with radiant, exotic structures, while others remain profoundly empty, echoing with quiet simplicity. What makes this idea so enthralling is that the rules we take for granted, the constants and laws that shape every breath we take, might not be universal at all. They might be local conditions peculiar to our bubble. Our physics may simply be one permutation from an endless list of possibilities. In that sense, our universe is not the universe. It is just one version of reality among many experimental drafts the multiverse has generated. And if you are wondering whether we live in a particularly lucky bubble, you would not be alone. Physicists often point out that the physical rules in our universe seem surprisingly fine-tuned for complexity. Not perfect, mind you. Gravity does not care if you drop your lunch, but balanced in a way that allows atoms to form, stars to burn steadily, galaxies to hold shape, and life to emerge. In multiverse terms, it is like we ended up with a recipe that actually bakes into something edible instead of exploding the oven. So, as strange as it sounds, we may owe our entire existence to the specific blend of cosmic rules that our bubble happened to adopt. Somewhere out there, other bubbles might be following entirely different rule books, some elegant, some chaotic, some downright unhinged. And in this grand cosmic collection, our universe is simply one bubble where the physics happen to be calm enough, stable enough, and perhaps friendly enough to allow beings like us to ask why reality behaves the way it does. In the multiverse, there is no single design. There are countless possibilities, each bubbling into existence, each experimenting with its own recipe for what a universe can be. And ours, for better or worse, is one where gravity behaves just reliably enough to keep us grounded, and only occasionally acts like a confused intern. If you have ever bumped into someone in a crowded hallway and exchanged that awkward half-apology, half-confused eyebrow lift, you already understand the basic emotional tone of universe collisions. Except in this case, the hallway is a vast multiversal sea, and the two individuals doing the bumping are cosmic bubbles the size of, well, everything. It sounds absurd, like something the universe came up with after staying up far too late. But in certain multiverse models, bubble universes could, in principle, expand into each other. And if they did, the aftermath might leave subtle clues, cosmic bruise marks, etched into the radiation that fills our sky. To appreciate how bizarre and dramatic such an event would be, imagine our universe as a giant, expanding balloon drifting through an endless balloon-filled warehouse. Most balloons never meet because the warehouse is expanding even faster than the balloons themselves. But if two manage to grow in directions that intersect, they might graze, rub, or collide at their boundaries. In human terms, it is an inconvenience. In cosmic terms, it is a collision between entire realities. The impact would not shake planets or cause stars to wobble. Rather, the collision would imprint itself on the earliest light our universe carries, the faint, ancient glow known as background radiation. Background radiation is like a baby picture of the cosmos. It is the oldest light we can see, the faint afterglow left over from the universe's early, hot phase. It stretches across the entire sky like delicate cosmic wallpaper. Tiny variations in this radiation tell us how matter was distributed long ago. Most of those variations are just normal, random patterns produced by early fluctuations. But if our universe had ever nudged shoulders with another bubble while both were still forming, that cosmic encounter could, in theory, leave a circular scar in the wallpaper, a bruise, a cosmic birthmark. a sign that something enormous pressed against our universe before the universe became transparent enough for light to travel freely. Physicists love this kind of idea because it turns the sky into a detective's notebook. If two universes collided, the energy at the boundary between them might have compressed or heated matter in our young universe in a distinctive pattern. That pattern could show up today as a ring-shaped distortion or a lopsided temperature shift in the background radiation. Not a bright, obvious fingerprint, more like a faint smudge you might see only with careful, statistical teasing. Think of it as the universe whispering, "Something bumped me once," in the quietest possible voice. Now, before you picture universes smashing together like two bumper cars operated by particularly reckless cosmic toddlers, collisions in this context are not violent impacts. They are more like gentle overlapping of expanding space-time regions. Universes are not hard shells. They are not solid balloons. Their boundaries are more like transitional zones where one region of space-time meets another. A collision would ripple through each bubble, but not in a way that instantly destroys everything inside. Instead, the interaction would subtly alter the distribution of energy in the affected region. Inside one bubble, say ours, the traces of this encounter might be forever frozen into the radiation that still surrounds us. This raises one of the most delightful scientific possibilities. Maybe we can look for these cosmic bruises. Maybe we already have. For years, researchers have sifted through high-precision maps of the background radiation, searching for oddities, circles, arcs, or temperature anomalies that do not fit the usual noise. A few features have sparked excitement, leading some to wonder whether they might be whispers of an ancient collision. But so far, nothing has been conclusive. Nature is tricky. Random fluctuations can masquerade as meaningful patterns, and the universe does not label its artifacts helpfully. Like, this is a bruise from Universe B. If a collision did happen, what would it feel like from the inside? For the first inhabitants of a newly formed universe, if such inhabitants existed, it might have seemed like a faint cosmic breeze, a directional distortion in how matter clumped or how space stretched. No galaxies would crash, no stars would swerve. Everything would form just slightly differently on one side than the other, as if the universe had developed a mild preference for one direction. Billions of years later, observers like us might notice that one region of the sky looks statistically odd, not obviously distorted, just different enough to raise an eyebrow. Some theories take this further. They suggest that the shape of our entire universe could have been influenced by a collision early in its inflationary period. If another bubble pressed against ours while both were still tiny, the compression might have squeezed our universe slightly, changing its geometry. The result could be a universe that is not perfectly symmetrical, but has a subtle directional tilt. That tilt, if it existed, might show up in patterns of background radiation that hint at an early cosmic encounter. Of course, this entire idea leads to a deliciously unsettling question. If our universe carries bruises, what happened to the other bubble? Did it drift away, forever out of reach? Did it continue expanding in its own direction, unaware of the tiny signature it left on ours? Or did the collision disrupt it so dramatically that it fizzled out, leaving behind no lasting form? In the multiverse, universes might interact only briefly before going their separate ways. Like ships passing each other in an infinite night. And then there is the ultimate twist. If collisions leave scars, then somewhere out there, in another bubble, beings might be scanning their own cosmic sky and spotting a bruise caused by us. They might look up and see an unexplained circular shimmer, wondering what touched their universe long before they arrived. Perhaps they imagine mythical cosmic beasts. Perhaps they imagine a divine tap. Or perhaps, just like us, they imagine other universes drifting through an immense multiversal ocean, occasionally brushing against each other in moments that leave faint but permanent marks. The idea that our universe might bear the memory of a collision changes the sky into a storybook. Every ripple of radiation becomes a potential clue. Every strange pattern could be the echo of an ancient interaction. And somewhere, if we look with enough care, the universe might be quietly showing us the bruise from the time it bumped into another bubble in the great dark sea of the multiverse. Imagine opening a cosmic map only to discover that instead of showing continents, oceans, or star systems, it displays a vast landscape of possible realities, each valley, hill, and plateau representing a different way the universe could have been built from the ground up. This is the string theory landscape, a theoretical terrain so enormous and varied that it makes our universe look like a single patch of grass in a planetary meadow. The idea behind it is simple in concept, yet dizzying in implication. If the fundamental constituents of reality are tiny vibrating strings of energy, then the way those strings vibrate determines everything: matter, forces, particles, and laws. Change the vibration pattern, and you change the universe. And there are a staggering number of ways these strings can vibrate. To understand the need for this landscape, we first step into the peculiar world of string theory. Instead of treating particles as tiny points with no size, string theory proposes that they are minuscule loops or strands of energy that vibrate like the strings of a violin. Each vibration mode corresponds to a different particle, the way each musical note corresponds to a different sound. A photon might be one vibration pattern, an electron another, a quark yet another. This alone would be a marvelous cosmic orchestra. But here is where the idea becomes truly overwhelming. The number of ways these strings can vibrate depends on the shape of extra dimensions curled up inside reality. Yes, extra dimensions. According to string theory, the familiar three dimensions of space, length, width, and height are not the whole story. Beyond them are additional spatial dimensions folded so tightly that we cannot perceive them. These hidden dimensions are like tiny origami structures woven into the fabric of existence. Their shapes determine the vibrational behavior of strings, which means they determine the entire physics of the universe that emerges from them. One shape might produce our familiar physics. Another shape might produce a universe where matter is unstable. Another could result in a cosmos built from bizarre particles we cannot even name. The number of possible shapes is so huge that even calling it astronomical undersells the situation. It is more like walking into a library containing more books than there are atoms in our galaxy. In this landscape, each possible configuration of these compact dimensions corresponds to a different vacuum state, a unique arrangement of energy that defines a universe. Some vacuum states give rise to universes with strong forces. Others give extremely weak forces. Some produce stable matter. Others do not allow atoms at all. Some might create universes that expand rapidly and cool slowly. Others might do the opposite. Each vacuum state is like a recipe card telling reality how to behave. Here is where things get truly wild. The landscape is not just enormous, it is populated. If string theory is correct, and the larger multiverse allows space to explore these different configurations, then each vacuum state could result in the birth of a separate bubble universe. The multiverse becomes a vast field of cosmic energy valleys, and space-time rolls into one valley or another, depending on tiny fluctuations or initial conditions. Once space-time settles into a valley, it stays there, shaping a universe with that valley's physics. Some valleys might be deep and stable, leading to long-lived universes. Others might be shallow, universes that form briefly and collapse almost immediately. Some might allow galaxies and stars. Others might never produce a single atom, remaining pure energy until they fade. In this terrain, our universe is just one valley, a comfortable one, evidently stable and calm enough for complex structures to form. But on either side of our valley lie countless others, each one representing a different universe with different laws. The strangest part of this whole picture is the sheer scale. The number of possible configurations in the string theory landscape is often estimated to be around 10 raised to the power of 500. That is a number so large that trying to write it out makes your brain file a complaint. To put it in perspective, if every atom in the observable universe wrote down a different number every second since the beginning of time, they would not even come close to counting that high. It is less a number and more a cosmic expression of good luck trying to comprehend this. With that many possible universes, the idea of fine-tuning takes on a new flavor. Instead of asking why our universe's physical constants seem so perfectly arranged for complexity, one could say that among a vast landscape of potential universes, some valleys naturally lead to stable structures. The fact that we live in one of the rare valleys where atoms form and stars shine is not surprising if there are unimaginably many other valleys where nothing interesting happens at all. In the multiversal view, our universe is not finely tuned. It is selected by the simple fact that observers can only exist in universes that allow them. But the landscape idea also raises unsettling questions. If every possible configuration can exist somewhere, does that mean there are universes where chemistry works backward? Universes where time evolves differently? Universes with entirely different types of matter? The landscape does not forbid such possibilities. In fact, it invites them. Some universes might have 4 dimensions of space, others might have 7, some might have forces we cannot describe. Others might lack stability entirely. In this dizzying terrain, our universe becomes a warm nook in a vast cosmic wilderness, a pleasant valley where matter forms structures, stars ignite, and minds eventually emerge to wonder how the whole landscape works. And if the landscape is real, then the multiverse is not just a collection of bubbles. It is a sprawling portfolio of possible realities, each one a different experiment in how the laws of nature can arrange themselves. The string theory landscape is not merely a theoretical curiosity. It is a reminder that reality might be far bigger and far stranger than our bubble alone suggests. And if each valley is a universe, then our cosmos might be just one melody in a symphony of countless vibrational possibilities, each born from the flicker of tiny vibrating strings. If the universe had a mysterious roommate, it would be dark energy, the elusive, unfathomable presence that quietly pays most of the cosmic rent, yet still refuses to explain what it does for a living. This strange something is responsible for the fact that the expansion of the universe is not slowing down, as you might expect from gravity constantly trying to pull everything together, but accelerating, as if the cosmos suddenly remembered it left the stove on and is hurrying to check. Dark energy acts like an invisible pressure woven into the fabric of space-time, gently pushing galaxies apart. And while we cannot touch it, hold it, or even fully understand it, some thinkers have wondered whether its peculiar behavior might be influenced by something outside our universe, something beyond the boundaries of our cosmic bubble. To understand this idea, we have to rewind to the moment astronomers realized the universe's expansion was speeding up. They expected expansion to slow over time, since matter should pull things inward, like a persistent cosmic tug-of-war. But telescopes revealed the opposite. Distant galaxies were drifting away faster and faster. It was as though the universe installed jet boosters without notifying anyone. Physicists invented the concept of dark energy to explain this unexpected acceleration, a placeholder term for whatever unknown process is driving the expansion. But dark energy has never been content to stay confined within tidy theoretical boxes. It behaves oddly. It seems consistent in strength across vast distances. It permeates all of space equally, refusing to cluster the way matter does. And it interacts with gravity in ways that feel almost too perfect to be coincidence. This puzzling consistency prompted some scientists to consider a radical possibility. Maybe dark energy is not just an inherent feature of our universe. Maybe it is influenced by forces bleeding in from outside, from the multiversal environment that surrounds our bubble. This is where things become beautifully mind-bending. In some theoretical models, the energy of the vacuum, the baseline energy of empty space, is not fixed. It can be affected by conditions beyond our universe. If our bubble is floating in a vast multiverse sea, then the shape, pressure, or dynamics of that sea could subtly tug on our vacuum energy the way tides tug on terrestrial coastlines. The result would be an expansion behavior that reflects not just what is inside our universe, but what lies beyond. Imagine our bubble universe as a balloon submerged in a fluid-filled tank. The pressure in the tank could affect the balloon, pushing or pulling, even if the creatures living inside the balloon can never see or touch the surrounding fluid. Likewise, dark energy might respond to the external pressure of the multiverse. If the multiverse has regions with different vacuum energies, the boundaries of our universe might feel slight imbalances, nudges that translate into the expansion rate we observe. These nudges could be incredibly subtle, like tiny whispers against the walls of our bubble, but on cosmic scales, even whispers can become significant. Another possibility comes from the idea that dark energy might be a kind of tension in the fabric of space-time, similar to the surface tension of a soap bubble. If different universes are like bubbles forming in a larger foam, each bubble has a certain amount of surface energy holding it together. That energy could influence the internal pressure of the bubble. In cosmic terms, the surface tension of our bubble could manifest as dark energy inside our universe, and if the surrounding multiverse has bubbles forming, stretching, or shifting near us, the tension might subtly adjust. The expansion we observe might be the internal expression of external geometry, cosmic architecture echoing across boundaries we cannot see. Some theories even flirt with the idea of multiversal fields, large-scale fields extending through the broader multiverse, bathing all bubble universes in a kind of shared energetic environment. These fields could influence the vacuum energy inside each bubble. If our universe is sitting in a particular region of this broader field, the local field conditions could define the amount of dark energy we experience. Move our bubble to another region, if such a thing were even possible, and the dark energy inside might shift. Fortunately, our universe does not go for long walks. The weirdness deepens when we consider that dark energy appears to have a constant density. As the universe expands, the amount of dark energy does not dilute the way matter or radiation does. Instead, new space seems to bring new dark energy along with it, keeping the density constant. This bizarre behavior aligns with the idea that dark energy might be the manifestation of a deeper external field, something that does not weaken as space stretches, because it is tied not to the contents of space, but to the very act of space-time being part of a larger structure. Could this external influence ever be detected directly? Probably not. Our cosmic horizon keeps the rest of the multiverse locked away from our view, but the signature of external influence might show up indirectly. For example, if dark energy ever changes slightly over time or varies in a way that does not match internal explanations, it could suggest that something beyond our universe is shifting conditions. Even a tiny deviation from perfect constancy would make physicists sit up straight, spill their coffee, and rewrite equations with trembling excitement. The most intriguing part of this idea is how it reshapes our cosmic identity. If dark energy is affected by external factors, then our universe is not an isolated island in a boundless sea. It is part of a connected archipelago, influenced by unseen tides, shaped by pressures and forces that extend beyond our cosmic shores. The expansion of our universe becomes not just an internal process, but a conversation, silent, subtle, and ancient, between our bubble and the greater multiverse around it. Whether or not this idea turns out to be true, it reminds us that dark energy, is far stranger than its name suggests. It is not darkness. It is possibility woven through space-time, possibility that might stretch all the way to the edges of other universes we will never see. Imagine for a moment that our entire universe, all the galaxies, stars, planets, atoms, and every awkward human moment ever experienced is painted onto an enormous, flexible sheet. This sheet stretches across a vast, higher dimensional space the same way a soap film spreads across a wireframe. Now imagine that our cosmic sheet is not alone. Other sheets drift nearby, each one carrying its own universe, its own physics, its own history. They move through a dimension we cannot perceive, like vast ships sliding silently through a fog so dense that none of the ships can see or signal each other. This is the essence of the brain world idea, one of the most imaginative offshoots of modern physics. The term brain is just a shortened version of membrane, but do not let the simplicity of the word fool you. In this picture, a brain is not a tangible surface like leather or plastic. It is a grand mathematical structure embedded in a higher dimensional space that physicists call the bulk. In this bulk, the familiar three dimensions of our universe are simply not the whole story. We see forward and backward, left and right, up and down, but there may be additional directions, hidden, silent, perpendicular to everything we know, where brains glide like cosmic rafts. Within this framework, everything we interact with, light, matter, forces, could be confined to our brain. Photons cannot slip off the surface. Atoms cannot fall through the cracks. Even gravity mostly sticks to the brain, though some versions of the theory allow gravity to leak a little into the surrounding dimensions, which might explain why it feels weaker than the other forces. If this is true, then we are not simply living inside a universe. We are living on a universe, a membrane floating in a higher dimensional expanse. Now picture the bulk, not as a void, but as an ocean of higher dimensional emptiness. It does not glow or ripple across our senses. It does not brush our skin or bend our light. But it may harbor countless other brains, parallel universes drifting like silent islands. Some brains may be close to ours, separated by a distance too small to imagine, but impossible to traverse, because movement between brains requires stepping into dimensions our bodies and particles are not equipped to access. Other brains might be drifting far away, unreachable in every sense. And each brain could have its own version of physics, shaped by how that membrane is curved, stretched, or energized. In some versions of brain world theory, the bulk plays a dynamic role. Brains can move within it, drawn by forces we cannot directly detect. They might warp or fold like sheets of fabric caught in gentle currents. And here is the part that transforms this idea from intriguing to downright cinematic. Brains can, in principle, collide. Not disastrously, not in a fiery explosion that obliterates everything, but in a grand world-making interaction. When two brains drift close enough to touch, their collision might release tremendous energy, sparking the birth of an entire universe on each brain. In this picture, the big beginning of our universe was not isolated. It was the echo of a brain-to-brain encounter, a cosmic handshake that set space-time ringing. If brains can drift, then their motions might create slow, rhythmic cycles. Perhaps our universe was born from a brain collision billions of years ago, and another collision could happen in the far future, long after all stars have faded. In this cyclic scenario, universes come and go like seasons in a higher dimensional landscape. While this idea is speculative, it offers a dramatic reinterpretation of cosmic origins. Our universe began not from a singular flash of nothingness, but from the moment two brains brushed against each other in the fog of the bulk. But even more fascinating is the possibility that nearby brains might influence ours without touching. If gravity can seep slightly into the bulk, then the presence of another brain could subtly warp gravitational behavior in our universe. Stars and galaxies might feel a ghostly tug from masses that do not exist within our cosmic sheet, but hover parallel to it on another brain. We would never see these masses. They would cast no light or shadow, yet their influence might whisper through space-time like the faint pull of a ship passing just beyond the fog. Some theorists have wondered whether the unexplained gravitational behavior in our universe, patterns that hint at invisible matter, might reflect shadows cast by another brain traveling near ours. It is a tantalizing idea. What if some of the mysteries we encounter are ripples from neighboring universes gliding silently beside us? The brain world scenario also suggests that the bulk itself could be far more exotic than the universes it contains. While each brain is tied to its own internal physics, the bulk might have entirely different rules. Particles that cannot escape our brain might appear as ghosts in the bulk, while forces that feel familiar on our brain might fade or behave unpredictably outside it. The bulk could be calm or chaotic, structured or fluid. We have no way to know because all our senses, experiments, and tools are trapped on our membrane. What makes the brain world concept so compelling is not just its exotic structure, but the way it reframes our cosmic perspective. Instead of imagining the universe as a solitary bubble drifting alone, we can picture it as one sheet among many, layered across a higher dimensional expanse. Our universe becomes less of an isolated stage and more of a floating platform, part of a vast harbor of brains quietly passing one another in the mist. And though we cannot see the ships around us, the possibility that they exist changes the entire mood of cosmic exploration. Instead of being alone in the dark, we might be part of a silent fleet, each universe sailing its own journey, unaware that just beyond the veil, other worlds drift by, each carrying its own strange cargo of stars and stories. Black holes already behave like the universe's drama queens. They devour matter, stretch time, twist light, and wrap space-time into shapes that would give even the bravest mathematician cold sweats. They are the cosmic equivalent of a "do not enter" sign, written in gravitation so intense it traps anything that comes too close. Yet some physicists suspect that black holes may not be endpoints at all. Instead of being the dark tombstones of collapsed stars, they might be cosmic maternity wards, cradles from which entirely new universes are born. It is a notion that flips the black hole story from grim finality to creative exuberance, turning gravitational collapse into the spark of cosmic genesis. To explore this idea, start with the basic structure of a black hole. When a massive star collapses under its own gravity, it compresses into an incredibly dense point called a singularity. The singularity sits hidden behind an event horizon, the one-way boundary beyond which nothing can return. Anything crossing the horizon falls inward toward the singularity, and to an outside observer, it appears to vanish from existence. But the singularity is not just dense. It is a breakdown of space-time itself. The usual rules, the tidy equations that describe how everything behaves, stop working. And when equations break down, theoretical physicists start sharpening their imaginations like chefs sharpening knives. Some theories propose that instead of becoming an infinitely dense point, the collapsing star triggers a dramatic transformation, the formation of a new region of space-time. In this picture, the singularity becomes the seed, not of destruction, but of a new universe. Think of a black hole as a tunnel, sealed on our end by an event horizon, but expanding on the far side into fresh, independent space-time. From the perspective of the new universe, the singularity might appear as its own version of a cosmic beginning, a kind of big birth that sets its space-time expanding. In other words, our universe's own big beginning may have been the other end of a black hole in some parent universe, where a collapsing star gave rise to our entire cosmic expanse. This idea takes the traditional concept of a black hole and turns it inside out, literally. The interior might open not into a crushing void, but into a relentlessly expanding universe with its own matter, energy, and laws of physics. Meanwhile, the event horizon cuts that universe off from ours, sealing the newborn cosmos within a boundary that cannot be crossed in reverse. Observers inside the child universe would have no way of knowing they began in the collapse of a star outside. They would simply see their universe expanding around them, filled with light, structure, and possibility. What makes this concept especially intriguing is that black holes are abundant. Our galaxy alone has millions of them, scattered through space like unopened cosmic seeds. If each black hole spawns a universe, then reality might be a branching family tree in which every gravitational collapse gives rise to a new cosmic branch. The multiverse becomes not a collection of independent bubbles, but a generational network, each universe producing others through the births of black holes, the way trees drop seeds that grow into new forests. And each child universe could, in turn, form stars that collapse into new black holes, generating new universes in a continually unfolding cycle. Some theories go even further, suggesting that universes capable of producing many black holes may be more likely to reproduce. In this scenario, the laws of physics within a universe can affect how many black holes form, which in turn affects how many new universes are spawned. This creates a cosmic version of natural selection. Universes whose physics favor star formation and collapse might produce more descendants. Over countless generations, Universes with physical laws optimized for black hole production might become the most common. It is an evolutionary take on the multiverse, the idea that our universe is the product of cosmic heredity shaped by the reproductive habits of earlier universes. Inside a child universe, the laws of physics might resemble those of the parent universe, but they do not have to be identical. The extreme conditions of a singularity could nudge the constants and parameters into slightly different values, creating a universe similar but not identical to its parent. Some daughter universes might collapse quickly, others might expand forever. Some might not allow stars to form. A few might be fine-tuned enough to support complexity, chemistry, or even life. We might inhabit one such fortunate universe, its constants inherited through a chain of black hole births stretching back through generations of cosmic ancestors. If this is true, then the collapse of a massive star is not the end of a story. It is the transition point between worlds. What looks to us like an object disappearing into darkness might look from the other side like the opening act of a universe's grand beginning. The singularity becomes a bridge, a funnel, a cosmic womb where space-time pinches and then stretches into new form. Of course, from inside our universe, we cannot peer beyond a black hole's event horizon. The geometry of space-time forbids it. Even if other universes exist within the depths of these gravitational giants, we would never see them directly. Our universe is self-contained, its cosmic horizon sealing us off from any parent universe. But the possibility that our universe was born from a black hole shifts everything we think we know. It turns black holes from cosmic trash compactors into portals of creation. It casts our universe not as the only universe, but as one link in an endless generational chain, and perhaps somewhere in another cosmos drifting far beyond reach, an ancient black hole once collapsed, triggering a burst of space-time that would one day host galaxies, stars, planets, and curious beings who would wonder about their origins, never realizing that their universe began inside the heart of a star that once shone in someone else's sky. If you have ever tried to bake something complicated, say a delicate souffle, you know that getting everything just right feels like begging the universe for a favor. A little too much heat, and it collapses. A little too little heat, and it never rises. A pinch too much salt, and suddenly it tastes like disappointment. In many ways, our universe looks like the ultimate cosmic souffle, delicately balanced, exquisitely structured, and stunningly responsive to tiny changes. The strength of gravity, the behavior of particles, the speed at which space expands, all of it sits in ranges that allow stars to shine, atoms to cooperate, and life to exist. Adjust any of these cosmic ingredients, even slightly, and our universe would become uninhabitable faster than a burnt souffle leaves the oven. This observation is what scientists call fine-tuning. The constants and laws of physics seem to land in the narrow space between disaster and possibility. But while fine-tuning has fascinated thinkers for decades, the multiverse idea flips the entire conversation on its head. Instead of asking why our universe is lucky enough to be balanced, the multiverse suggests that perhaps this balance is simply inevitable in at least one universe, if enough universes exist. It is the difference between winning a lottery once and winning a lottery that is being played an infinite number of times. You would expect someone, somewhere, to win, and it just so happens that we are living in the winning ticket. To appreciate how dramatically the multiverse reshapes fine-tuning, consider how we interpret the universe's physical constants in isolation. If there is only one universe, and its constants cannot vary, then their life-friendly values look almost suspiciously perfect. Why does matter clump instead of drifting apart eternally? Why do stars ignite at just the right temperatures to fuse elements without instantly blowing themselves apart? Why does chemistry, the strange dance of electrons, work so well that it can build everything from mountain ranges to microbes to grandmothers who refuse to share their secret recipes? In a single universe view, these coincidences feel astonishing. They border on eerie. But in a multiverse, they become as ordinary as buying a pair of shoes that just happen to fit because the store has thousands of sizes. The multiverse reframes fine-tuning not as a cosmic miracle, but as cosmic selection. If countless universes exist, each with different values for the constants of nature, then most of them would indeed be barren. They would expand too fast or too slow. They would fail to form atoms or stars. They would be filled with radiation instead of matter, or matter instead of structure, or structure instead of complexity. In such a vast landscape, the vast majority of universes would never form anything more interesting than a bland soup of particles. But buried somewhere in that enormous collection would be a few universes that accidentally land on the right combination, not because they were chosen, not because they were intended, but because mathematical possibility guarantees that with enough tries, you eventually stumble onto something that works. In this view, our universe is not special because it is fine-tuned. It is special simply because we are here to observe it. We could not have evolved in any of the universes where things fall apart before stars are born. We could not contemplate physics in a universe with no atoms. We would not exist to take notes in a universe where chemistry cannot form molecules. So of course we find ourselves in a universe that is comfortable. It is the only type of universe where beings like us could ever arise to ask the question. This idea is sometimes called the observational selection effect, which is just a fancy way of saying that you only ever wake up in a place where waking up is possible. You never find yourself in a universe where life cannot form for the same reason. You never find yourself magically appearing in the vacuum of outer space. It is not a survivable environment. The multiverse does not tell us that our universe was designed for life. It tells us that in a large enough collection, life inevitably ends up in a universe that allows it. This shift in perspective can feel liberating or unsettling, depending on your philosophical tastes. For some, the multiverse removes the need to treat fine-tuning as an extraordinary mystery. It becomes a statistical inevitability. For others, it raises deeper questions. If our universe is not uniquely crafted, then what does that say about purpose, meaning, or specialness? Are we cosmic accidents living in an accidental universe within an accidental collection of universes? Or does the sheer vastness of possibility make our existence feel even more extraordinary? Not because we were chosen, but because reality is broad enough to allow beings like us to emerge at all. There is also a quiet elegance in the idea that the laws of nature might not be fixed across all reality. They might be the local rules of our particular cosmic neighborhood, much like peculiar zoning laws that apply only within city limits. In another universe, hydrogen might behave differently. The speed at which light travels might be slower or faster. Forces might not balance in the way they do here. Those universes would be strange and inaccessible, yet they would share a conceptual kinship with ours, siblings shaped by the same overarching mathematical framework, each one running its own version of reality. Thinking this way shifts fine-tuning from a question of, why is the universe like this, to, in a multiverse, how many ways can universes be? And suddenly the rare, delicate balance we see becomes not a miracle, but the result of a cosmic lottery that had more than enough opportunities to produce at least one ticket that allowed stars, chemistry, and eventually creatures who invent espresso machines. The multiverse does not make our universe less meaningful. It simply widens the lens through which we view it. Instead of seeing our cosmos as the lone precious jewel in a dark void, we see it as one gleaming stone in a vast mosaic of realities, each one different, most inhospitable, but at least one hospitable enough to ask how the mosaic was assembled. And that, in its own quiet way, feels like a kind of cosmic wonder. If the multiverse exists, it is the most spectacularly private thing imaginable. It is the neighbor who always keeps their curtains closed, the co-worker who never reveals anything personal, the cat who sits just out of reach and watches you silently, but refuses to interact. The multiverse, if real, is hidden behind layers of cosmic encryption so tight that the universe itself enforces them. Still, despite these heavy privacy settings, physicists have not given up hope of finding faint, indirect hints, little breadcrumbs scattered at the edge of what we can observe, not enough to prove anything definitively, but enough to make the universe feel like it is dropping subtle hints just to tease us. Hunting for multiverse evidence is like trying to detect a gentle breeze by studying the motion of a single grain of sand. It requires creativity, persistence, and a willingness to stare at data so abstract it might as well be written in ancient runes. But that does not stop the scientific imagination. Researchers have come up with a surprising assortment of strategies, some bold, some cautious, and some that sound like the universe dares you to attempt them. One of the most tempting ideas is to study the background glow left over from the early universe. This light, which blankets the sky, carries an immense amount of information about the cosmos when it was young. If something unusual pressed against our universe or interacted with it before it finished forming its structure, then the imprint might linger in this ancient glow. Scientists search for patterns that should not be there, symmetries that look too perfect, shapes that look too deliberate, or anomalies that whisper, "Something nudged reality before you arrived." Each surprising wiggle in the radiation map becomes a puzzle piece. Is it a random fluctuation, or is it a smudge left behind by a universe brushing ours long ago? Then there is the idea that the constants of nature might subtly reveal a multiversal origin. If different universes have different physical rules, then the set of rules in our universe might not be perfectly rigid. They might shift slightly or leave faint irregularities in their wake. Perhaps the strength of a force is not totally uniform across all space. Perhaps certain regions hold tiny differences that cannot be easily explained by conventional physics. If such irregularities appear, they might serve as cosmic fingerprints from whatever shaped our universe in its earliest moments. It would be like finding a faint watermark on reality, hinting that it once passed through an environment with different rules. Another approach involves searching for unexpected gravitational patterns. Gravity, unlike light, is stubborn and subtle. It is influenced by every chunk of matter and energy, even the invisible ones. If something beyond our universe exerts a tiny gravitational pull, something outside our cosmic bubble, but close enough to tug ever so lightly, it might cause slight distortions in how galaxies move or cluster. These distortions would not shout, they would barely whisper, but with enough precision and enough patience, physicists might detect anomalies in motion that cannot be explained by anything inside our universe. It would be like noticing a ship drifting slightly off course because of a wave you never saw coming. There is also the possibility of discovering unexpected energy signatures, faint clues buried in the behavior of the vacuum itself. Empty space is not truly empty. It seethes with restless energy that flickers constantly. If the multiverse influences this vacuum energy, even in a tiny way, then the patterns of those fluctuations might reveal something unusual, something that does not quite match the predictions of a universe sealed entirely within itself. Detecting such irregularities would require measurements so precise that every experimental physicist involved would need lifelong supplies of strong tea. But the possibility remains open. More speculative ideas push the boundaries of imagination. Some theories propose that particles might occasionally behave in ways that suggest they were influenced by dimensions we cannot directly access. Perhaps a rare event in a particle collision might look as if something slipped briefly into another realm before returning. Perhaps a peculiar type of energy loss in a high-energy experiment might hint that part of a process leaked into a higher dimensional space. These ideas belong to the realm of daring theoretical exploration, the kind where the line between brilliance and madness is thin, but the potential payoff is extraordinary. Even if direct detection of another universe remains impossible, the patterns in our universe could serve as indirect testimony. If certain cosmological puzzles refuse to resolve using internal explanations, the suspicion grows that an external influence might be hiding behind the curtain. Like detectives, physicists look for inconsistencies in the story the universe tells. Does something feel forced? Does a model require too many patches to make sense? When the internal evidence becomes twisted, the possibility of an external cause becomes enticing. Yet for all these possibilities, the multiverse remains elusive. Every promising lead comes with challenges. Random fluctuations often masquerade as meaningful patterns. Noise in data can mimic structure. Nature loves misdirection. The cosmos has a habit of giving answers that solve one question only to generate 3 new ones. And the vastness of space is filled with so much complexity that separating signal from noise feels like trying to listen for a whisper during a thunderstorm. But scientists are stubborn. Curiosity is relentless. As technology improves, so does our sensitivity to the universe's faintest murmurs. Future telescopes might detect patterns in radiation we cannot see today. Future particle accelerators might probe the vacuum with unprecedented depth. Future gravitational wave detectors might pick up the slightest distortions from realms outside our own. Each technological advance sharpens our cosmic senses. The real challenge is accepting that the multiverse may leave only indirect evidence, suggestive clues rather than definitive proof. It may never announce itself clearly. It may refuse to step into the spotlight. And yet, even a handful of subtle hints would change everything. They would whisper that reality is bigger, stranger, and richer than the boundaries of our universe suggest. They would hint that our cosmic bubble is not the full stage, but one part of a vast, layered theater. So we continue to observe, to analyze, to dream, and to listen. We look into the sky not expecting certainty, but hoping for a hint, a little glitch in the cosmic privacy settings that reveals the presence of other worlds drifting beyond our reach. If you have made it this far, your imagination has already traveled through inflationary booms, drifting brains, cosmic collisions, and gravitational gateways. You have toured universes with bizarre physics, watched randomness sculpt reality, and peeked at the possibility that our bubble universe is just one shimmer in a vast cosmic ocean. By now, you might feel as though the universe has gently taken your sense of normalcy, patted it on the head, and whispered, "Oh, you sweet summer child." But that is exactly what pondering the multiverse does. It stretches the mind until the familiar shape of reality dissolves into something far stranger, far larger, and far more exhilarating. At first glance, the multiverse sounds like a cosmic escape hatch, a way to plaster over mysteries by saying, "There are lots of universes, pick one." But that is not the heart of it. The multiverse is an invitation to step back from our instinct to see the universe as a single, privileged story. For most of human history, we thought Earth was the center of everything. Then we discovered it was one planet among many. Later, we learned our sun was one star among billions. Then our galaxy, one island among uncountable others. The multiverse continues that long tradition of cosmic humility. It suggests that even our entire universe, the stage on which every human drama has ever played out, might be one small piece in a tapestry so vast that calling it vast feels more like a polite understatement. This shift changes more than just scientific curiosity. It changes how we think about our own existence. In a single universe worldview, everything we experience is part of one grand, tightly knit narrative. The physics we observe must apply everywhere. The constants we measure must be fundamental. The beginning of our universe must be the beginning of everything. It is a tidy worldview, compact, elegant, and reassuring. But the multiverse shakes that confidence. It suggests that our universe might not hold the monopoly on reality. There could be universes with different stories, different laws, different ingredients, and different possible outcomes, all equally real, all equally monumental in their own right. This realization is not meant to make us feel insignificant, although it certainly tempts that interpretation. If anything, it gives our existence a new kind of significance, one defined not by being central, but by being improbable and precious. In a multiverse, life arises only in universes where conditions happen to fall into a narrow range. That means our universe is special, not because it was chosen, but because it managed to craft the delicate conditions necessary for complexity to emerge. We become not anomalies, but natural consequences of the universe's capacity for experimentation. Reality becomes a cosmic laboratory, and we are one of its most intricate results. The multiverse also expands our sense of possibility. When we look at our universe through telescopes, we witness a single version of the cosmic story, a narrative shaped by our particular blend of physics. But if countless universes exist, then every variation of physical law that can exist somewhere does. Somewhere there might be universes filled with strange forms of structure, with physics that give rise to unimaginable patterns. Others might be barren but beautiful, with elegant geometries sculpted by forces unlike any we know. Some might evolve slowly, quietly, with no stars or matter at all. The multiverse is a cosmic library of realities, each one its own volume, each one containing a different expression of what existence can be. Pondering such a library makes our bubble universe feel both smaller and richer. Smaller because it is not the totality of reality. Richer because its story gains depth when seen against the backdrop of what might lie beyond. A painting hung alone is one thing. A painting hung in a gallery becomes part of something larger. The multiverse turns our universe into a gallery piece, unique, intricate, and meaningful in ways that go beyond itself. It also deepens the mystery of existence. If our universe is one bubble among many, then the question, why is there something rather than nothing, becomes layered. Perhaps the multiverse simply exists because reality cannot help but express itself in every possible way. Or perhaps the multiverse is a natural consequence of deeper mathematical principles we have barely begun to understand. Or perhaps existence is not a single answer but a sprawling landscape of answers, each tied to a different universe. Oddly enough, knowing that we might never have a final explanation makes the story more fascinating. Mystery is not a flaw in the cosmos, it is a feature. What makes the multiverse idea so compelling is not that it guarantees other universes exist, but that contemplating it changes our perspective, even without proof. It reminds us that the universe does not owe us simplicity. It does not owe us comfort. It does not owe us answers that fit neatly into human intuition. Instead, it invites us to imagine boldly, to wonder freely, and to embrace the possibility that reality is stranger than any story we have told so far. And here is the quiet truth at the end of this long adventure. Even if we never detect another universe, never see a bruise on the cosmic sky, never catch a gravitational whisper from the bulk, never sense the tug of an unseen brain, the act of imagining the multiverse reshapes us. It widens our cosmic self-awareness. It teaches us that our bubble is not the limit of what might be, and it humbles us in the best possible way, reminding us that the universe we call home might be just one shimmering world, drifting in a vast and silent ocean of possibilities. So when you look up at the night sky, you might feel the smallest tug of wonder, a whisper that our universe is part of something much larger, much stranger, and profoundly more imaginative than anything we once believed. The multiverse turns the cosmos into a grander story, and we, living inside one delicate bubble, get to be part of that story, even if we never see its full scope.